Hey, what's up guys, this is Dr. Vivek Balipuram bringing you the next lecturette in ECPE 127, Random Signals. In this lecturette, I'm going to find the expected values of x and y and the variances of x and y for this particular joint PDF. And then I'll also evaluate the covariance term and the correlation term. For you, I would like for you guys to solve part A for Monday's class. So for Mondays, or rather for Monday, I would like for you to submit it by 5 p.m. on Canvas. Remember that we are not meeting on Monday. We are just going to review through our videos, lecture videos, and we are going to work on these problems. On Wednesday's class, however, I'll be holding a review session for those individuals that are wanting to take midterm number 3. And midterm number 3 sign up sheet will be up soon. So without further ado, let's solve the problem part B here for fxy is equal to 8x, y for x between 0 to y, and for y between x to 1. So we need to find expected value, variance, and covariance and correlation terms. So fxy in this case is 8xy. It's 8xy for this particular region. For this region, and x is greater than or equal to 0 and y is greater than or equal to 0. So we need to find expected value of x and expected value of y. Before we proceed ahead and find the expected values of x and y, I think it's a good idea to first evaluate the marginal density functions of x and y. So everything begins with the evaluation of the region of non-zero probability, which is this region right here, for which the PDF is non-zero. So let's evaluate the region of non-zero probability, or rather let's plot the region of non-zero probability. Both x and y are greater than or equal to 0, so that means I'm looking at my very first quadrant right here, and I have this relation that x is less than or equal to y, and which is in turn less than or equal to 1. So everything is within this small square here between 0 to 1. So let's plot the equality relationship x is equal to y. So this is the equality relationship x is equal to y. I'm interested in the region that x is less than or equal to y. So this point right here is 0, 1, which satisfies this condition that x is less than or equal to y. So this shaded region right here is the region of non-zero probability. So that is step 1. Now, if you recall from my previous lecturette, to find the marginal density functions, we would typically integrate the joint PDF with respect to the other random variable, and the limits are in this case, how does y vary in this region? Or rather, for a given x, how does y vary in this region? That's the question that we'll ask ourselves, and to identify the limits of integration here. So if I were to ask you this question, for any value of x, how does y vary? So well, y varies from x all the way to this point, y is equal to 1. This is how y varies in this particular region. So the PDF of x is obtained by integrating 8xy with respect to y. The limits are from x to 1. Now, because this is the non-zero probability region for my original joint PDF, now since I have integrated y out, I'll eliminate y from the region of non-zero probability. So whatever equation that I get, that will be the marginal PDF of x, which will be valid for, or which will be non-zero for this region. So f of x is, I have 8x y squared over 2, and the limits are from x to 1. 2 and 4 simplify to 4x, and I get 1 minus x squared. 4x times 1 minus x squared for x between 0 to 1 and 0 otherwise. So that is the marginal PDF of x. Similarly, I can get the marginal PDF of y by integrating the joint PDF with respect to the other random variable x. So I'll redraw my region of non-zero probability, because when we find marginal PDFs, this is a reset process. Everything is reset, and we are going to evaluate, or we are going to identify the limits of integration afresh. So this is the region of non-zero probability. And here we have to ask ourselves, for any y, how does x vary? How does x vary? And we'll identify the limits as, for any y, x varies from 0 all the way to y. So the limits are from 0 to y, 8xy dx. And because I'm integrating x out, x will disappear from the non-zero probability region. It will disappear from the non-zero probability region. So all that will remaining is the marginal PDF of y. So I get, when I integrate with respect to x, that is x squared over 2. 2 in the denominator cancels partially the 8, giving 4 x squared times y, and the limits are from 0 to y. So I get 4y cubed for this region, 0 to 1, and it is 0 otherwise. So that's the marginal PDF of y. Right, okay. So once I have identified the marginal PDF of x and y, I can use them to calculate the expected values. So expected value of x will be integration from, typically from negative infinity to infinity, x times f of x dx. F of x here in this case is 4x times 1 minus x squared dx times this x here, giving me x squared. And I'll integrate this, and the limits will be from 0 to 1, because this PDF is non-zero between 0 to 1. And when I solve this integral, there's many methods in which I can do. So I get 4x cubed over 3 minus 4 over 5 x to the 5, and the limits are from 0 to 1. When I plug in a 1, I get 4 over 3 minus 4 over 5, which is 8 over 15. 8 over 50. That's the expected value of x. Now let's get the expected value of y. Expected value of y is y times f of y dy. So y times 4y cubed dy. And the y in this region varies from 0 to 1. So this PDF is non-zero between 0 to 1. So when I evaluate this integral, I get this 0 to 1, which is 4 over 5. So that's the expected value of y. I can get variance of x as expected value of x squared minus expected value of x whole squared. So expected value of x squared is integration x squared times 4x 1 minus x squared dx, and the limits will be from 0 to 1. So when I evaluate this integral, I get 4x to the 4 over 4 minus x cubed x to the 5, so 6, 4 over 6 x to the 6, and the limits are from 0 to 1. So I get 1 minus 4 over 6, which is 2 over 6, which is equal to 1 over 3. So variance of x will be 1 over 3 minus 8 over 15 whole squared, so 1 over 3 minus 64 over 225. When I solve this, I get 675. 225 minus 12, 192. 25 plus 8 gives me 25 plus 8 gives me 33 or 675. So that's the variance. That's the variance of x. Similarly, you can get the variance of y. I would like for you guys to get the variance of y. You do not have to submit it, but for the time's sake, I'll not solve variance of y. Or you know what, let me just do that. Let me just solve variance of y for you too. So to get variance of y, first I need to get expected value of y squared, which is y squared times 4y cubed dy. The limits are from 0 to 1. I get 4 over 6 y to the 6, 0 to 1. So 2 over 3 is the expected value of y squared. So variance of y is 2 over 3 minus expected value of y whole squared, which is 4 over 5 squared. So I get 2 over 3 minus 8 over 25, giving me 50 minus 24, which is 26 over 75. So that is the expected value. That's the variance of y. Similarly, I need to get now the covariance term and the correlation term as well. Now, covariance term is obtained in a simple manner. Let's see how we can get the covariance term now. Covariance of x and y. So I'll erase this part and to evaluate the covariance of x and y. Okay, so covariance of x and y is actually expected value of x minus mu of x times y minus mu of y. So that is xy minus x times mu of y minus y times mu of x plus mu x mu y. So that is expected value of xy minus, I will get mu x mu y minus mu x mu y plus mu x mu y. So these cancel out. It gives me expected value of xy minus mu of x mu of y. We already calculated the expected value of x and y from before. So let's just focus on getting the expected value of xy. Now to get the expected value of xy, I actually need to rely on my joint PDF and not the marginal PDFs, because now I have a function that is of both x and y. Now if you recall, my joint PDF is 8xy for x between y to 1, or rather for this region, x greater than or equal to 0, y greater than or equal to 0. So this was the region of non-zero probability. This was the region of non-zero probability. And I need to double integrate xy times fxy over this region of non-zero probability. So here, I'll use the same principles of finding the limits for probabilities. When I devise the limits for finding the probabilities, I'll use the same methodology. So I'll ask myself in this region for any x, how is y varying? So y is varying for any x between x to 1. That's how y is varying, x to 1. And then once I have integrated y out, what is the minimum value of x in this region and what is the max value of x in this region? When I ask these questions, the minimum value of x is equal to 0 and the maximum value of x is 1. So 0 to 1. So notice that the limits of outer integral are all constants. So this integral will evaluate to a constant, which is expected value of xy. Once I find the expected value of xy, I'm going to plug it in this equation right here and get the covariance term of covariance between x and y. So the value of covariance is going to tell me whether x and y are increasing or decreasing with respect to each other or not. Notice that expected value of xy is actually a correlation term as well. Expected value of xy is also correlation. Okay, so I will let you guys practice evaluation of the integrals here. So you can go ahead and evaluate. The key lesson from this lecturette is to how to appropriately evaluate the limits of integrals. So now for Monday's in-class participation, again, there's no virtual meeting, or we are not meeting on WebEx on Monday, but you are going to submit by 5 p.m. the expected values of x and y, variance of x, variance of y, the covariance term, and the correlation term, expected value of xy for part A right here. All right, and you're not just going to give me the limits of integral, you're also going to give me the actual numerical values. Please pay careful attention to finding the limits of integral. Then for Wednesday's class, in-class participation by 5 p.m., you need to get the covariance and correlation term for this problem right here. For this problem, get the covariance term and the correlation term. And that will be due for Wednesday by 5 p.m. So I repeat, we are not meeting on WebEx on Monday, but there's going to be an in-class participation problem due at 5 p.m. We will be meeting on Wednesday at 2 p.m., which will serve as your midterm 3 review. Now that WebEx session is also optional, and it is meant for those individuals that would like to take midterm number 3. So by Monday 5 p.m., you're also going to let me know that whether or not you're going to take your midterm number 3. I'm going to send out a poll which will ask you whether you're taking midterm number 3 or not. Please answer that poll, and that will help me prepare my lecture for Wednesday's class. Again, Wednesday's class is optional and only for those individuals that would like to take midterm number 3, but all are welcome to participate. All right, guys, I'll sign out.